Okay, so now we have to make a group. So third week of semester, and everyone is fixed. The registration is fixed. So I think it's a good time to make a group. So as I said, we're going to have 2 projects throughout the semester, and this is project-based class. The first project is making a quantum simulator. The reason why we are doing this project, quantum simulator, is best way to learn something is to make something. Okay? So if you want to understand quantum algorithm, quantum gates, or whatever, you have to be able, if you make one, or in this case, you cannot make quantum computers. So if you make a quantum simulator, then I think that's the best way and fastest way to understand the quantum computing. So I want to ask if you want to make your own group on your own, or if you want to randomize the group. So raise your hand if you want to pick your own group member. Okay, there's some people who wants that. So so apparently this is a paper used for other class, but I want you to use the back of this paper to write your name and mark your friend's name together by connecting lines or circle it with a big circle, so that you can indicate which person you want to be in the same group. So write your name and then, or you can write your friend's name together so that you want to be in the same group with someone else. Yes. Well, depends. So 3 to 5, around 3 to 5. Okay. So I'm going to pass the paper and the pen. So meanwhile, we're going to talk about the quantum gates, and I plan to do one more slide because we have a holiday next week on Wednesday. So we're going to cover most likely three lectures in 2 days in this week. Okay, so while we are talking about the lecture, you can pass your paper and then write your name together. Okay, so quantum gates. Now we are in a real quantum computing business. So there are basic gates and there are some special gates. So basic gates are X, Z, and Y gates. These are basically the same action of Pauli X, Pauli Z, Pauli Y. However, in the real quantum computer, Y gate is not implemented because XZ, if you put XZ together, then you get Y. So basically X and Z are the main gates. And you can represent these gates in many different ways. One way is using 2x2 matrix. Another way is Ketra notation like this. And you can see that these are the operators. These are unitary operators. And unitary operators can be implemented in quantum. These gates can be implemented in quantum computer. Okay, so other gates are Hadamard gates, and this is very important gate. And this is basically send ket 0 to ket plus and 1 ket to ket minus. And you can represent this as a 2 by 2 matrix like this, or you can represent as a sum of two gates, x and z. So for this lecture, we're going to try represent operator like h in the linear combination of other gates. However, when you try to implement it into a quantum circuit, you may not implement this type of linear combination of two or more gates in a circuit because it's not allowed to add two quantum states. You can make a superposed state applying a certain gate, but you cannot simply take two quantum states and add together. It's not possible. That's not, physically possible. So this is just an ideal representation. So just meaning that it's a operation. And there are gates such as phase shift gates, and I represent it as R theta, and theta goes to here, so right here. So it's a 2 by 2 represented by 2 by 2 matrix of diagonal matrix. And if you apply this, then obviously 0 ket is always 0 ket, but it only changes the 1 ket, and it changes the phase of 1 ket. So if you have a multiple of e to the minus I phi, then it shifts the phase by theta. So that's why it's called the phase shift gate. So if you change your phase by pi, which means if you take the r pi, it's exactly same as z. So in other words, you change a phase of 1 ket, leaving the phase of 0 ket the same. So that's the action of z gate. But if you change your phase by pi over 2, then you get a different gate called S, and basically it's the square root of Z. So that's another notation representing this S gate. And you can also shift the phase by pi over 4. Ideally, you can do it forever. Like any angle, you can choose for the shifting angle. And there are names for these special angles, S and T. All right, so we're going to talk about S and T more often when we deal with the Shor algorithm later, or Groover's algorithm. But right now we're not going to use this S and T. We're only concentrate on 3 gates: X gates, X gate, Z gate, and Hadamard gate. Okay, these 3 gates are the basic gates. Okay, so these gates act on 1 qubit state. How about we talk about 2 qubit gates? The gate acting on 2 qubit state. So easiest way to make a 2 qubit gate is that you multiply or tensor product 2 1 qubit gates. For example, you can apply X gate on the qubit 1 and Z gate on qubit 0. So you can separate out an action of these gates into 2 different 2 qubit gates. For example, you can apply Z gate on qubit 0, and then you apply X gate on qubit 1. So when you apply Z gate on qubit 0, you don't do anything on the qubit 1. So you can imagine that you're applying identity gate on qubit 1 in that case, and then when you apply the X gate on qubit 1, you don't do anything on the qubit 0, so you're assuming that you're applying identity gate on qubit 0. However, you can do it at the same time. You can apply the gate at the same time. So it really doesn't matter because it doesn't affect. So even if you apply gate on the qubit 0, it doesn't affect the state on qubit 1. right? So it only applies to qubit 0. So you can take these two gates separately and then write it in this way. So actually it doesn't matter if you switch the order of these two gates, because it acts on different qubits. So this is actually same as that 0, x1, so on. So that's a 2-qubit gate, but that's actually same as applying 1-qubit gate. However, there are genuine 2-qubit gate called C0 gate. That's a really important gate here. So it is a gate acting as follows. So you're applying basically X gate, but not always. It depends on what's the state of the controlled gate, a controlled qubit. So we represent the C0 gate as C0x1, meaning that the qubit 0 is the control gate and qubit 1 is the target qubit. So qubit 0 is the control qubit, and here x1, the qubit means that qubit 1 is the target. Okay, target qubit. So based on the so depending on the state of controlled qubit, if it's a qubit at the state cat1 state, then you apply X gate on the target qubit. If it's a state cat0, then you don't do anything on the target qubit. So it's a 2-qubit state, so it changes the 2-qubit state. So you can represent this C0 gate as 4x4 matrix. So basically, if you have 0, 0, so this is the qubit 0 and this is qubit 1, by the way. So that's represented by 1, 0, 0, 0, right? So when you apply C0x1, now the target is qubit 0. It's in the state cat 0, so you don't do anything on the target qubit. So it goes to 1, 0, 0, which is same as original state. So how about when you have like 1, 0 here? So again, the qubit 0 is in the state cat 0, so you don't do anything on the target qubit. So originally it's a 0, 1, is it? Yeah. No, sorry. So it's 0, 0, 1, 0. So it goes to 0, 0, 1, 0 again, which is same as 0. And okay, so how about 0 now 1? So this is 0, 1, 0, 0, right? So here, so I think I made a mistake in this representation. Anyway, let me check again by taking a calculation. So now in this case, qubit 0 in the state of cat 1. That means I'm going to apply X gate on the qubit 1, which is the target. So this goes to 1, 1, because that's applying X onto the 0 state, cat 0 state. So that's same as 0, 0, 0, 1. Right? So how about 1, 1? So this goes to, so this is 0, 0, 0, 1, and this goes to 0 tensor 1, which is same as 0, 1, 0, 0. Right? So now you have the action of your 2-qubit gate, C0 gate, on 4 basis vector on the 4-dimensional space. So 1, 0, 0, 0 goes to 1, 1, 1, 0, 0, 0, 0. So it goes to 1, 0, 0, 0. So, and then let's take this one. 0, 1, 0, 0 goes to 0, 0, 0, 1. So 0, 0, 0, 1. And the third one, this one, maps to 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0. And the last one, this one goes to this. So it's 0, 1, 0, 0. So I made a mistake here. So it's a 0, 1, 1, 1, 0, 0. So I think you get the original matrix if you switch the target and the control qubit index here. So anyway, this is C0x1. Okay. You can also represent the same C0 gate using the linear combination of other gates, like this one. So here 1 means identity gate. So instead of writing as I, it's easier to write it in terms of 1. And also you're multiplying x1 here. So in this case, so x1 times 1 is x1, and x1 times z1, z0 is same as 2-qubit gate, like this one. So we will talk about why you can represent your C0 gate as a linear combination like this. So after we talk about the number gate. So let's talk about a little bit more a general form of controlled gate. So instead of having C0 gate, so here not means that you're inverting 0 and 1, you're interchanging 0 and 1. That's basically the same as the classical NOT gate, right? That's why it's called controlled NOT gate. But instead of applying X according to the controlled state, you can apply U, which is the unitary gate, whatever that is, and define a controlled U gate. So if you do that, then instead of putting x1 here, you can put u1 here to represent the same thing. So now, if you want to represent it into matrix form, it depends on what your unitary gate is, but you can always represent it as a 4x4 matrix. Another type of gate is a swap gate. It basically swaps the state. So if you have 0, 0, then, so basically it swaps the qubit 0 and 1. So 0, 0 goes to 0, 0 because, switching the 0 cat together is same as 0 cat again. So 1, 1 also is not changing anything because 1 cat is switched to 1 cat. But here, if you have a different state in between 2 qubits, then you get swapped. States are swapped. 0, 1 becomes 1, 0, and 1, 0 becomes 0, 1. Right? So that's why you get these first row column and last column remain the same, but these second and third are swapped here. Okay? And you can also represent this swap gate in terms of linear combination of x and y, and in this case, y gates too. Okay, well, we'll talk about this, why we can represent as a linear combination. Let's look at the number operator. So this is not a real operator because this is not unitary. So by the way, this is not a unitary, which means that you cannot implement this number operator in any of quantum computer. However, this number operator is useful to represent your gate or operator in terms of linear combination of other gates or operator. So number operator sends 0 to 0 vector. So it's cat 0 to 0 vector, so it annihilates the 0 cat, and 1 cat to 1 cat. So basically this number operator n is represented by 0, 0, 0, 1. Okay? Obviously it's not unitary. So if you want to represent this as a linear combination of basic gates, then this is the way you can represent. So you can simply calculate this matrix multiplication, matrix summation. So 1, 0, 0 minus 1 gives you 1 over 2, 0, 0, 1 over 2 times 2. So therefore you get this one. And also you can invert this. So meaning that you have n tilde given by 1 minus n. Here 1 again is the identity operator. To get, now in this case, the n tilde sends 0 to 0 and 1 becomes 0 vector. Okay, so it's an opposite. So this can be written as 1 over 2, 1 plus set. Now, here's a way you can actually represent your 2-qubit gates using number operator. So suppose that you're swapping the qubit I and qubit J. It's same as doing this. Okay, same as the linear combination of these. So I'll give you time to think about why this is true after we look up all the slides content here. And also you can represent your CNOT gate in this way. So first you take the tilde on I, which is the controlled qubit, and then you also take the I's qubit and then take the number operator and then apply the X gate on J's qubit, which is the target qubit. So that's one way you can talk about you can represent your 2-qubit state. And there are more types of gate. It's n-qubit gates. The typical example is Toffoli gate. Now, Toffoli gate acts on 3 qubits. It acts on 3-qubit state, and it contains 2 or more controlled qubit. So in this case, we're taking C0 and C1, which means that qubit 0 and qubit 1 are both controlled gate. And X2 means that qubit 2 is the target qubit. So we apply X only when the qubit 0 and qubit 1 are in the state ket 1. So if either of these two controlled gate is in the state of ket 0, we don't apply X gate. Okay? So if you want to represent into matrix form, now it's a 3-qubit gate, so it acts on 8-dimensional vector space. So it can be represented as 8 by 8 matrix like this. And there are easier way to represent this in terms of number operator. So that's your task today, to find out how you can represent your Toffoli gate, like C0, C1, X2, in terms of linear combination of number operator or the X and Y and Z gates. So you can think about the number operator also in terms of n-qubit acting on the n-qubit state. So for example, if you have a n-qubit state represented by number, actual number, X, range from 0 to 2 to the n minus 1, then the number operator acting on this n-qubit state is defined by this way. So basically 0, so number operator on n-qubit state acting on 0 ket gives you 0 vector, and number operator on 1 gives 1. And how about 2? So 2 is 2 times 2. So 2 here basically means that you have all 0, but the last 2 qubits are 1 and 0, right? And so on. So you move on like this one. So you can also make this type of number operator on n-qubit state with combination or just multiple of number operator all acting on 1-qubit state. So this we're going to do together today. All right, so we're going to go back to the slide, some part of the slide again, and then do it together. But before we do that, is there any questions you want to? Is there any part that you want to see more or need more explanation? Yes. It's 3? Okay.
Matrix is different.
Which this matrix is coefficient. Square root, right? No, is it? Yeah, square. I forgot. Yeah, there's a typo. Square root. Yes. Thank you. Any other question? Yes.
Entire
CNOT gate.
especially the phrase that apply X gate to the top.
Apply X gate to the target. So what does that mean? So let's talk about. So can I make a new? Let's see if I can make a new note. No, maybe not. Let me open up another note here. Okay. So instead of C0x1, let's talk about C1x0. So I'm going to give you a picture, which is actually official notation for C0. So this is qubit 0, and this is qubit 1. Oh, by the way, so this is opposite. This is X, and this is. So maybe it's better to have this pictorial description of the CNOT gate. So the wire, horizontal wire, represent the qubit. So it's basically a timeline for qubit. You may think of this as a timeline for the qubit. So let's see, I started my 2-qubit state with, let's see, first qubit 0 is initialized as qubit 0, cat 0, and the qubit 1 is initialized at cat 1. So what happens is, okay, so time moves this direction, and the control qubit picks up the qubit state, and it reads that the qubit is in the cat 1 state. Now, it activates this X gate on the qubit 0. Okay, so, sorry. Oh, I was right. Oh yeah, that's right. The C1X0, yes. Therefore, it acts X gate on the qubit 0, right? So after this point, if you want to measure, if you measure the qubit on the qubit 0, what will be the outcome is not 0, but 1. Okay? So you can measure any of this qubit state. So let's see, if I measure this part, then it reads as 1. Okay? So this symbol, looks like an odometer is a measurement. It represents the measurement. So if I don't apply C1X0 CNOT gate, then what happens is I have the same 2-qubit state initialized as 0 and 1. And if I take the measurement on both qubit, I get 0 and 1. Okay? So, of course, a measurement is always probabilistic, and also there's an error, but we're talking about ideal situation that the quantum states are cat 0 and cat 1, and it's like this one. So every time if I don't apply C0 gate on this state, I always get 0, 1. But if I apply the C0 gate, then I get 1, 1 instead. So that's the C0 gate. So you can do the same thing with a different initialization. So for example, if I have 1 cat and 0 cat here, and I have the same C0 gate here, and let's try to apply, that's after applying the C0 gate, let's guess what will be the outcome after the measurement. So the C0 gate matches the control gate with the state cat 0, and it means it don't apply the X gate on the qubit 0. So therefore, there's no application of X gate here. So even though it's there, you see that it's connected to the control gate, so it's not activated. So it's still in the cat 1 state. Therefore, if you read the quantum state of the qubit 0, it's still 1, right? And it's 0. Because you don't do anything on the control gate. So it's always the state the same. But in this case, the control gate is in the cat 0 state. So the target qubit, it's not changed at all. So it's still 1, 0. So you want to see the other version of the explanation? Did that,
Honestly,
okay.
I don't understand why in that case X gate is not activated.
Why not activated
In that case.
in this case? Because it's 0.
Also control.
Yes, it's because of the state of the control qubit. Okay, so how about let's do some example here. So here's an example. What will be if you apply the C0 gate on here? Zero control. So let's compute the result. So maybe you can throw in the coefficient 1 over square root of 2. Question?
0, 0, 0.
0, 0, 0, 1. You want a little bit thicker? Is it too dim? Or
This one,
okay. How about, I think it's not about color. I think about thickness. Maybe. That looks better. Okay, let's do it together. Is there anyone compute already? Anyone tell me what the result is? Anyone? Not done yet? Have you done yet? So how about it? I'll give you time to discuss with your friends next to you. So if you got the answer, or if you don't know how to get the answer, talk to your friends. By the way, is there? Where's the paper? Can I get the paper back? Does everyone write your name here? Does everyone write your name? You didn't?
Didn't write my name.
Okay.
I think.
Anyone else? Let me know if you didn't write your name yet. You didn't? Okay. How about you talk to your friend next to you? 됐어요?
저거 혹시 몇 명부터 몇 명까지인가요 혹시?
3 to 5. 3 to 5. It's okay not to have a group yet. I'm going to randomize the group. So just taking the preference, who you want to work with. Okay. Okay, so let's talk together. How about group 2? Do you have a conclusion? Okay, so can you tell me what the result is?
Same as
The same thing? The whole thing? Oh, by the way, this is the qubit 0. Okay, so you start from the right.
0, 0, 1.
Okay. It's not hard, right? 0, 0, 1, 1. Anyone familiar about this state? There's a reason why I'm using this state. Anyone familiar about this state? Anyone heard about the Bell state? Bell state? Anyone heard about the Bell state or entangled state? Actually, that's the stuff that we're going to talk about today or maybe tomorrow.
State that cannot be represented by.
Right. What is special about this? So, okay. So here's the circuit. So actually what I do is here's the qubit 0 and qubit 1, and I start from cat 0 for both state, and I applied Hadamard gate on the qubit 0, and then apply controlled X. Oh, by the way, the controlled X often represented as this also. And then I get this state. So whatever that is, it's right here. So this is supposed that if I put it this in psi 2, then at this point, this is the state, psi 2. So what happens is, if I take a measurement on any of this qubit, let's say here. Now, so it means that I take the measurement of the qubit 0 first and then take the measurement of qubit 1. So what will be the measurement of qubit 0? What are the possible outcomes? 0 or 1. So what are the, oh yeah, I didn't mention the bonus rule. So there are both chances that you can see 0 and 1. Let's say you pick up the 0 for the outcome. What will be the outcome of the qubit 1 in this case? 0. Why can't you see 1 as an outcome for the qubit 1? Because if you took the measurement of qubit 1 first, you could have seen 0 or 1, right? But if you took the measurement of qubit 0 first and then take the measurement of qubit 1, then your measurement outcome is fixed to 1, fixed to 0, right? So somehow, the measurement of the first qubit, the qubit 0, affects the measurement of the qubit 1. It seems like it affects, what is it? It's somehow the measurement on one qubit affects the measurement outcome of the other qubit. Well, mathematically, it's nothing special about this. But if you think about this in a practical sense, let's say you prepared two qubit physically and then applied Hadamard gate and controlled NOT gate and made the two qubit state like this. And then you take these two qubits far away each other, and then now you take the measurement. So one person with one qubit takes the measurement, you got 0. Okay, other person will always observe 0, right? So depending on the observation of the one person, the person who takes the measurement next will be fixed. The outcome will be fixed. So a little bit awkward. Let's say if you're taking these two qubits apart by light year, like long distance. After this person takes the measurement, immediately the next qubit, the second qubit, has a fixed outcome, right? So somehow you can imagine that there is a, you can imagine there is a information delivered or information is transported from one qubit to another faster than light. It's not even faster than light. It's immediate transmission of the information. That's really contradicting to the special relativity, right? So it's not. It's an interesting phenomenon, but it's not the way you should interpret this phenomenon. And we're going to talk about this. We were going to talk about this shortly after next. Oh, it's gone already. So we're going to talk about this shortly. Okay. All right. So that's easy relatively. So let's talk about the other part. All right, how about this one? So let's check why this is true. Okay. I think, so since I made there's a typo here, maybe it's better to walk through together why this is true. So we're going to use the number operator, as I mentioned here. Let's talk about that way. So, okay, C0x1. So, let's see. I want to keep the 0 cat on the qubit 0, but I want to do something if it's cat 1 on qubit 0. So if I apply the number operator on 0's qubit, then I only keep the qubit 1, cat 1 state and annihilates the cat 0 state, right? So this N0 keeps cat 1 on qubit 0, annihilate cat 0 on qubit 0. Okay, and let's think about this one. So it's opposite. So it keeps cat 0 but annihilates cat 1, opposite. So I want to, mix these two to have the action of this CNOT gate. So how can I do this? So if I see cat 0 on the qubit 0, I want to keep the identity matrix, identity operator. But if I see the cat 1, then I want to have X gate survive. So if I take X1, let's see. Right, there's no other way I can just express in the symbol. So that's the idea. So so if I take, so here, let's see, plus sign here. So I want something going on here. I want to multiply something on here. So let's call it A and B. So, okay, so I'm going to apply this to somehow this qubit 0 state. The qubit 0. It's cat 0 state on qubit 0. So that gives me what? So if I apply this cat 0 on here, this will vanish my operator A, right? Because number operator kills the cat 0, right? But if I apply this to here, it will survive and leaves the operator B, right? So same thing with cat 1 on qubit 0 will make A survive but kills B, right? What do I require for B and A? So if qubit 0 is in the cat 0 state, that's the control state, it means do nothing on the qubit 1, which means that it's applying, same as applying the qubit 1, identity operator on 2 qubit state. So this should be identity operator. And if the qubit 0 is in the cat 1 state, I want it to be X gate. Actually, X gate on qubit 1, right? Okay, so now what is it? So therefore, C0 X1 should be X1 times N0, just identity, but identity is just same as 1, so N0 tilde. And X1 is X1. What is N0? So N0 is 1 minus Z0. And N tilde is 1 over 2, 1 plus Z0. Right? So this is same as 1 over 2 X1. Let me put it this way. So 1 over 2 plus 1 over 2 X1 plus 1 over 2 Z0 minus 1 over 2 X1 Z0. Okay? So how you have to interpret these operator is, these are all the 2-qubit states, 2-qubit operators, sorry, 2-qubit operators. So this identity operator is a tensor product of identity operator on acting on each qubit. And this one is X gate on qubit 0, identity on qubit, X gate on qubit 1, identity on qubit 0, and identity on qubit 1, Z on qubit 0, and then X and Z, like this one. So let's now make it into representation of matrix. So this one is 1, 1, 1, 1. So how about this one? So you're taking a tensor product of these two matrices. So the rest of the part is here. So 1, 1, 1, 1. And the second one is now 1, 1, 1, 1. See what it means? It's a 4 by 4 matrix, but identity matrix are in the off diagonal position, like this. So and how about the third one? So you get 1, minus 1, 1, minus 1. Then what's the next? 1, minus 1. I should put it here. 1 minus, and it's x minus x tensor z. So 0, 1, 1, 0, tensor 1, minus 1. So this becomes 1, minus 1, 1, minus 1, right? So let's add all together. So the first one is simply adding these one and these one, but you have a 1 over 2 multiplied, so you get 1. Then how about, okay, so off diagonal. So you have off diagonal 1, 1 here. Again, another 1, 1 here, but you have a negative sign, so it becomes 0 and 0 here. So nothing in here anyway, so it's all 0. And how about the second diagonal entry? So it's 1 minus 1 minus 1, so it's 0 again. And how about the third diagonal? 1, here we get nothing, right? Here we get 1, and here's nothing. So it's 1 plus 1 divided by 2, so we get 1 here. Okay, we're almost done. So how about the last diagonal? So we have 1 and minus 1, so it goes 0. What left is actually here and here. So look at these places. So here we have 1, 1, and we have minus 1, minus 1. But we have minus 1 over 2 multiplied. So we get actually 1. So we get 1, 1 here. So rest of the entries are all 0. So we get the same 4 by 4 matrix we computed before. Okay? So it's not the matrix representation. So I'm emphasizing that you can make your CNOT gate as a linear combination of this number operator by think about how this CNOT gate act on each qubit. Okay. Any question before we move on? So we are going to use this number operator to represent other, like a swap gate and so on. Okay, so how about we talk about swap gate? Here we have a swap gate. So here. So if I apply S01, so meaning that I and J are both 0 and 1, and this becomes N0 and 1, and tilde 0 and tilde 1, and X1, X0, it doesn't matter, the order doesn't matter, X1, N0 and 1 plus N tilde 0 and tilde 1. Okay, so prove why this is true. Prove why you can represent your swap gate as a linear combination of operator like this. Let me know if you have any question. Yes.
Confusing about the concept of two qubit gates.
2 qubit gate. Okay.
It used to control the two qubit system which have one
That's a 1 qubit.
two of them.
Okay.
So, I think if you want to make some product to two of them, you should use something like the sum, not the sum, but the combination of the two matrices, which have.
So you can represent 2 qubit state as 4 by 1 matrix,
4 by
right?
1 matrix.
So if you represent your 2 qubit gate as 4 by 4 matrix,
Yes.
you can multiply that 4 by 4 matrix to 4 by 1 matrix like this. So that's way you can, one way you can calculate the action of an operator. Or if you have a tensor product of two 1 qubit gates, 1 qubit state, then you can split it into some of basis state 0, 0, 0, 1, 1, 0, 0, 1, 1, and then apply this 2 qubit gate on each base state and then see the result. We can, you want to go through the example together, but like this one? Want to see an example?
So, if I could see, it would be great.
Okay. Okay, so after we talk about the swap gate representation, we'll talk about the example. Okay. All right, so whether you finish or not, how about talk to your friends next to you? Think about why, how you thought about the proof, which part you didn't understand clearly. So it's the talking helps. If you talk to someone else, it actually helps to figure out which part you didn't understand or to understand better if you already understood. How about you guys sit together? Can you move one? Can you move your seat here? I think there's some typo here. I think there's a typo. I think I have to calculate by myself, but we're gonna do it together. But keep in mind if some keep in mind that there could be a typo in this expression. Yes. Yeah. You wanna have you talk talk together, talk to each other. Do you have a question?
I don't know how to start
How to start?
this like this form.
Mm-hmm.
I don't know why we have to get started on this.
Okay, so you have to start from what's the meaning of this operator? N0, N1. What do they do?
Uh,
So
on
it,
and
yeah,
off
uh-huh.
by the state of these two qubits.
Hmm?
Two qubits, zero
Yes.
qubits and one.
Right, 0 qubit and 1 qubit. And it acts on each qubit separately. But it's an annihilation. So it annihilates cat 0, right? So when does this operator makes the qubit state survived?
So we started this this song or in like it's like some product because of these two qubits are both on this operator.
It's a product, but
Um,
not just this one. It's some of these ones. But let's first think about the action of this operator, Ni and J. So you can start applying 0, 0, 0, 1, 1, 0, 1, 1 on this operator and then see what's the outcome.
then when the operator operates on two qubits both to lead, then we start some this formula with making this formula with this like this formula.
Right, right. I mean, you have, if you want to write the swap gate as a linear combination of these operator, you need to understand what each operator are meant to do. So let's start from the meaning of this operator. So, okay, have you found the typo here? Group 2, where is the typo?
Last one.
Yes.
Till
Here the how should be changed. In
I changed the first one. And I
change how?
swap
Swap? I mean, how do we swap? NINJ, swap NINJ? Ah, this one. Right, so it's not the same NINJ, NINJ tilde. It's a NI tilde NJ, NJ tilde, NJ, NI, NJ tilde. So the tilde, the position of tilde must be switched. Okay. So let's, anyone wants to talk about why? So let me show you the correct form. So this is the correct form. Does anyone want to talk about why this is true? Like this one, why this works? Is there any group want to talk about why? Okay, so it's very simple. Group, what was it? 4? You want to talk about why? Let me show you the picture again. So, do you want to explain?
제대로 이해한 건지 모르겠는데 세 개랑이 더해져 있는데 경우의 수에 따라 가지고 둘 다 1인 경우에는 첫 번째 항만 나머지 둘은 0이 돼서 날아간다고 두 번째 항 둘 다 0일 때만 나머지 두 항이 0이 됐어요. 1형이거나 0, 1인 경우에는 위에 n0 tilde n1이나 n0 n1 tilde 둘 중에 하나가 1이 돼가지고 x0 x1이 돼서 두 개가 섞이는 방식으로 작동을 한다고.
Right. Anyone understand what he said? Everyone understand what he said? Right. So basically, the number operator acts separately. So when I apply n0 and 1 on 2-qubit state, there are 4 possible 2-qubit state: 0, 0, 0, 1, and 1, 0, and 1, 1. So if it acts on 0, 0, what happens is n0 and n1 kills the cat 0, right? So it kills both of these cat state. Okay, so it's 0. And how about this one? So n0 acts on cat 1, so it survives. It keeps the cat 0. But n1 acts on cat 0, which kills the cat 0. So basically, it's a 0 vector tensor with, so let me write it, 0 vector tensor with cat 1. It's 0 vector. So anything tensor with 0 vector is 0. So the same thing applies here. So it's 0. So it's all 0 vector. So the omni-cat state, omni-base state that survive after applying this number operator is 1, 1 state. It goes to 1, 1, right? So I want to do this for other states. So if I take 0 and tilde 1, then it keeps the, 1, 0 omni and kills the other. It kills all the other base states. It only keeps this state. So what I want is, if this is our input state, then I want to swap into 1, 0, right? That means I have to apply X gate and on qubit 0 and qubit 1. So therefore, which means that I have to apply this gate, this 2-qubit gate on here. So that's why I have to multiply these 2-qubit state with number operator like this. So that should be one part of our swap gate, and the other part is the same thing. So that's all encoded in here. So I want to keep 1 1 0 0, but if I encounter 0 1, so actually qubit 0 and qubit 1, and 1 0, then I have to apply this 2-qubit gate. That's all. So if you want to further write your swap gate in terms of X and Z gate, now you can replace your AND gate, the number gate, with this identity, and tilde with this identity. So for example, if I, this one can be written as 1 over 2 I minus at 0 times 1 over 2 I minus at 1. So this means 1 over 4 I minus at 0 z 1, minus z1 plus z0 z1. Okay, so this one term is written as the sum of 4 operators, and you can do for same thing for other, and you can write in terms of only in terms of X and Z gates. Okay, so any other questions? Everyone understood what's happening here? Okay. So we can work on topology gate, but we want to talk about examples. So what was the question? What was the example you wanted to see? 2-qubit gate acting on 2-qubit state. Okay. So I want to clarify with an example how 2-qubit gate acts on 2-qubit state. So for example, let's say I'm going to, let's say, give an example of Z0. So just a random example. So X1 here. Okay. So let's say I have this unitary gate. And it's not a unitary gate. It's just a whatever operator. It's an operator. Just an operator. I want to find out my action of this operator. Let's see. On these 2-qubit states. So I'm giving you a tensor product of two 1-qubit state, and I want to figure out this. So there are two ways to approach this. One is you can rewrite your qubit state into superposed state of base state like this one. So first it's 0 0 1 0 and 0 1 1 1, and then you apply your operator on each base state separately and then add them together all together to get your final state. Or think about the operator itself. The operator U itself is a sum of operator, which is given by 2-qubit operator. The first one is Z operator on qubit 1, X operator on qubit 0. And the second sum is I identity on qubit 1, but Z on the qubit 0. And the third one is Xi, right? So you can apply each operator on this 2-qubit state separately and then add them together. So let's do that way. So first, Zx applied to 0 plus 1 tensor 0 minus 1 is defined by applying the gate on qubit 0 on qubit 0 state, gate on qubit 1 on qubit 1 state. So Z on 0 plus 1, tensor X on 0 minus 1. So what is the result? So 0 is 0, 1 is minus 1, that's a Z gate, and X becomes swapping 0 and 1. So that's the result. So applying Z tensor X on the quantum state, the 2-qubit state, gives you this state. But that's not all. That's one part of your operator. Now let's apply this. So we have I, Z acting on the same. So imagine this one is right here. So we're not doing anything on the qubit 1, so it remains the same. But on the 0 qubit, you get Z operator. So tensor 0 plus 1. Okay, so that's the second one. And how about Xi? So you get the same state. Now you only apply the X on the qubit 1. So you get this. Okay, so you can simply add all this up, or just leave it as a summation of these qubits as a superposed state. That's your result. Okay. Okay, before we finish, I can see there are some people who wants to be grouped with together. If you have, so I'm not going to finalize the group today. So I'm going to wait until this week, Friday. If you have any change of plan of grouping yourself into someone else's group, then let me know on Friday class. Otherwise, I'm going to keep the same group as possible. You gave me here, but rest of the students will be randomized, so that they're going to be in a group of 3 or 4, or maybe 5. It depends. But I want to keep the group of 3 or 4. 5 is a little bit big. So yeah, I hope this is everyone. So if there's someone who missed this class, then I will ask this again on Friday. So after this week, we're going to finalize the group, and keep always in mind, whatever, now what you have to keep in mind is how you're going to design your simulator. So as I mentioned before, as I shown you before, there are quantum composer designed by IBM that is graphic composer of the quantum circuit. That's one way you can make your quantum simulator. So graphical design, graphical user interface might be one way to go, or you can make a quantum simulator package. You can write your code in Python or any other language. So you can make a package providing a simulator of quantum computer. So for example, Qiskit is Python package made by IBM that can be used for simulating quantum computer and quantum circuit. So you can look up how Qiskit works, and then you can try to do the similar or make it better in your own purpose. Or somehow, like 2 years ago, I had a group who designed on hardware. It's not a real quantum computer, but the hardware that mimics the quantum computer. So actually, inside of that hardware, there is a quantum simulator. So you can try to design on hardware that works as if it's a quantum computer, which means that it simulates a quantum computer. So whichever ways, you have to think about how you're going to make your product. So once we finalize the group this week, from next week, we're going to discuss about, I'll give you the time to discuss about your first project, making a quantum simulator. Okay, so if you have any other questions, let me know. We didn't go through the second slide, but we'll do it next time. And yeah, if you have any question, let me know. See you on Friday.